When two black holes collide, they send ripples through space and time, much like waves, spreading across a pond. These ripples, known as gravitational waves, were first predicted by Einstein in 1916. However, it wasn't until September 2015 that the Laser Interferometer Gravitational Wave Observatory, LIGO, finally detected them, confirming one of the most profound aspects of Einstein's theory of general relativity. Detecting gravitational waves presents a colossal engineering challenge. To capture a wave as vast as our solar system, scientists must measure changes in distance, smaller than the width of an atomic nucleus. Yet, with instruments like LIGO in the USA, Virgo in Europe, and KAGRA in Japan, we've been able to detect these elusive waves, particularly from violent cosmic events, such as black hole collisions. Now, researchers from the Okinawa Institute for Science and Technology, OIST, along with colleagues from Tohoku and the University of Tokyo, have made a groundbreaking proposal. They suggest that cold atoms, in a quantum state known as a Bose-Einstein condensate, can simulate gravitational waves in the lab. This revolutionary idea was born from their work in studying quantum matter, and their findings were published in Physical Review B, selected as the editor's choice. Einstein's theory of general relativity transformed how we think about space and time, explains Professor Nick Shannon, senior author of the study. He goes on to say that while gravitational waves contain crucial information about the universe, observing them remains one of the toughest challenges in science. To circumvent this, the OIST team discovered that certain quantum phenomena involving cold atoms and magnetic systems could serve as an exact analog to gravitational waves. This result is important because it provides a simpler way to simulate and study these waves, says Professor Han Yen of the University of Tokyo. The implications of this research could help us better understand the real gravitational waves traversing the universe. At the heart of this discovery lies a quantum state called a spin-nematic phase. We've been studying these for a while, says Professor Shannon, likening them to the nematic phases used in liquid crystal displays, LCDs, of smartphones and televisions. Unlike LCD molecules, however, spin-nematics support waves that behave just like gravitational waves. Dr. Lily Chouinowski, the lead author, was thrilled to bridge two seemingly different branches of physics. "I've always been fascinated by the beauty of physics," she reflects, especially when you can connect phenomena through similar underlying mathematical structures. The team's work offers a promising new approach to understanding one of the universe's most mysterious forces, from the comfort of a laboratory setting. Thanks for watching. If you are new to our channel, please subscribe to our channel and turn on the bell for further notification.